Everybody, let us talk about Deutsch quantum algorithm, and further we will also discuss about Deutsch Jozsa quantum algorithm. Quantum algorithms outperform classical ones because they use principles like superposition, entanglement, quantum interference to process many possibilities at once. Instead of checking each input one by one, as the classical algorithms do, quantum algorithms explore multiple outcomes simultaneously and use interference to amplify the correct answers and cancel out the wrong ones. This parallelism actually allows them to solve certain problems like factoring large numbers, searching databases, or identifying patterns much faster than any classical method. Now, in this lecture, we will first of all take a very simple case which actually demonstrates the quantum advantage over the classical methods. And then we will, in the Deutsch Jozsa algorithm, we will take a slightly complex problem, similar problem but slightly complex, and we will see how the quantum algorithms give us the quantum advantage. Now, to start with, the let us have the problem definition. Um Given a function f that takes a single bit as input, now there is a function f that takes single bit as an input and yields a single bit as an output. Now, so this is how the definition of that function is. Our goal is to determine whether the function is constant or balanced. Now, a function is called constant if it produces the same output regardless of the input it receives. So, irrespective of any type of input, it will produce a constant output. So, in the case whether the input is 0 or 1, the output will be either 0 or 1, fixed for both the inputs. So that's the definition here. Constant fx is equal to fi for all xy. That means the output is constant for any input. Now, what is the balanced function? Balanced function, fx is 0 for half of the possible inputs and fx is equal to 1 for other half of that means for one half of the inputs the output will be let's say either 0, and for the rest of the half the output will be 1, or vice versa. Now let us consider all the cases here. So when case 1 and case 2 belong to actually constant functions, in which, let's say, input is 0, output is 0, input is 1, again the output is 0. So that's a constant function. Similar is the case here. Input is 0, output is 1, input is 1, output is 1. Now in the case of the balanced function, half of the times for half of the inputs the output is 0, for the rest half the output will be 1. So that means case 3 and case 4 belong to the balanced functions. Now, quantum versus classical solution. As I was just trying to introduce at the beginning of the lectures, to solve this case, in the classical method you will have to make two calls to the function. If both the outputs are same, f will be considered constant, otherwise it is termed as balanced. So you need two calls in the classical case. But in the case of quantum, you need only one call to the function, because the function is called only once, as it employs the superposition of all the possible inputs. This superposition speeds up the quantum algorithm. Now let's draw the quantum circuit for Deutsch algorithm. It takes, so let us, so this is the quantum circuit that will actually perform the job of solving this problem. Now, how the initialization is done? So we will take an input ket 0 and the other, actually this is an ancilla qubit. So this is initialized to 1. So this is our actual input initialized to 0, which is ket x. So ket y is the ancilla qubit actually. Now this is ket 0 is passed through the Hadamard gate and ket 1 is also passed through the Hadamard gate. So So x basically, ket x is basically the equal superposition, and ket y is also the superposition. Let us divide the whole circuit into stages, and let's see the output. Let us see the status of the quantum bits, qubits at every stage. So ket psi 1 is, this is the tensor product between ket 0 and ket 1. After that, the two Hadamard gates will come. So ket psi 2 is at this point, is the second stage. So ket psi 2, this is the ket 0 plus ket 1 divided by under root 2. This is for ket 0, and for ket 1 it is ket 0 minus ket 1. So just solving it further, we will get this expression. Now, what is ket psi 3? So this is the quantum oracle that actually for ket x it gives the same input is repeated. For the ancilla qubit, this fx XOR with y. So this is actually the operation that is performed. Now this is the quantum oracle. Now what this quantum oracle will do basically, so this is the ket psi 2 quantum status of the quantum system at the second stage, ket psi 2, right? So ket x is the first qubit and fx plus y is the second qubit. So this is 0 here, so it will come straight as it is. That's what this quantum oracle is doing. So for ket x, the ket x is, we are getting ket x as it is. So this first qubit will come as it is here. For the second qubit, if you look at the quantum oracle, it is fx plus y. So what is our x? X is 0, so fx will be f0 plus 0. So y. So our first qubit is 0. So that means fx plus 0 will be, this is our second qubit. So fx is basically, because x is 0, so therefore f0 plus 0. In the second case, here x is 0 but y is 1. So therefore f0 plus 1. In this case, our x is 1. So f of 1 plus, because y is 0, so f of 1 plus 0, like this. So this is how the oracle, and what is the output of the oracle? We have ket x, this is ket x, and this will be the ket of fx plus y. So that's the output of the quantum oracle. Now let us consider some cases. Let's say we are let's say f0 is equal, let's say we are looking for if the function is, let's say, constant function, f0 is equal to f1 is equal to 0. So we apply this condition, this case here into this equation, and what we get is finally we get this particular output at ket psi 3. So that means in the quantum circuit, at the ket psi 3, the ket psi 3 is the quantum state after the quantum oracle. So this is our ket psi 3. This is our ket psi 3. Then we pass the first qubit through the Hadamard gate. So this is our first qubit. It is passed through the Hadamard gate. The second qubit is as it is. So this is basically when ket 0 plus ket 1 under root 2 is passed through the Hadamard gate, actually we will get ket 0 and the second qubit will be as it is. And if you see the quantum circuit, then we measure the first then we measure the input qubit, that means ket x. So when we measure this qubit, we will get 0. So what is the claim? As I just explained here, if you measure 0 in the first qubit, the function must be constant. So as we supposed it to be, as we gave f0 equal to f1 equal to 0, that means it is a constant function, and that's what our claim. If we measure 0 in the first qubit, the function will be constant. So we supplied the inputs for constant function and we got 0 at the first qubit. So that means our claim is proved, which says that our function is constant. And the same circuit can be tested or for the other types of functions also, like f0 equal to f1 equal to 1 also. Here in this case I took the case of f0 equal to f1 equal to 0, but you can take other cases also. And for the balanced function you can also verify the output. In the case of balanced function, f0 equal f of 0 will be equal to 0 or f1 will be equal to 1. So that means half of the inputs will be 0. For half of the inputs the output will be 0. For the rest half the output will be 1. So if we consider all the cases, the circuit will perform absolutely wonderful. And if it measures 0, if the first qubit measures 0 on measurement, the function will be constant. Otherwise the function will be a balanced function. Now in the Deutsch algorithm we gave only see here we gave only one qubit as the input, but in the case of Deutsch Jozsa algorithm we will give n qubits as the input and the output will be only 1 qubit. The output will be basically if the function is whether the function is a constant function or a balanced function. But in this case the inputs will be input will be an n qubit input. The problem remains the same. A function is considered constant, so we know what is a constant and a balanced function. So let us consider, if let's say we gave 2 qubits as the input, let us see the options. Now if we give 2 qubits as the input, that means what can be the combination? 0 0 0 1 1 0 and 1 1. So in the case of constant function, either for all the inputs the output is 0 or 1. So that this is a constant function. And in the case of balanced function, for half of the inputs the output will be 1, for half the output will be 0. So all these cases actually determine whether the function is a balanced function or not, because if you look at the output, half of the output will be 1 and half of the output will be 0. So this is a balanced case, right? Now if we want to if we want to know the status of this function through classical means, so because we must check half of the total inputs, right? So if we get for half of the inputs, let's say half of the inputs are 0, right? And if the next input that we are checking is also 0, right? So it will be when we check half of the inputs as 0 and the next input is 1. If we check half of the inputs and for half of the input, let's say the output is 0, but for just the next qubit the output is 1, in that case the function doesn't remain a constant function, it will be a balanced function, right? So in the worst case, for the n qubit input we will have to how many combinations are possible, how many inputs are possible? 2 raised to the power n inputs are possible in this Deutsch Jozsa algorithm. We must check half of the inputs. That means 2 raised to the power n is the total number of inputs, divided by 2 is half of the inputs, and if we check plus 1 inputs, so that means we can know whether the function is a constant function or a balanced function. So therefore it is actually 2 raised to the power n minus 1 plus 1. So if we try to portray the complexity of the classical computing, it is big of 2 raised to the power n. So this is an exponential time complexity. But if we so this is through the classical means, if we try to verify through classical computing. But if we do it through the quantum computing, only one call to the oracle will tell us whether the function is constant or a balanced function. So time complexity in the case of quantum computing is O to the power 1. So this is the perfect example. This algorithm is a very good example to show that the performance of the quantum computers as compared to the classical computing. Look at the complexity, compare the complexity of the two cases. One is O to the power O of 2 to the power n, that means it's a complex exponential time complexity. Here it is constant, almost a constant O of 1 time complexity. So this is a huge advantage that we get if we try to solve the problems through the quantum computing. We get an exponential speed up. So that means the query complexity is one of the type of complexity that so this is the oracle and this is the algorithm. If we make one call to the oracle, that will be treated as one query, right? So just as I was trying to explain here the complexity, we will have to make how many queries? We will have to make half plus 1 queries to the oracle to get the answer whether the function is a constant or a balanced function, right? So this is the quantum oracle. In this case, similar to the Deutsch algorithm. In the Deutsch algorithm, the input was only a single qubit input, but in the case of Deutsch Jozsa algorithm, the input is n qubits, and there is a single qubit ancilla qubit, and the outputs are also similar. We will get the input, we will get the same input here, and we will get 1 qubit output, which is basically fx plus y. So in the step 1, we will initialize it to we will initialize the n qubit register to all zeros. So that's what is done here, initialize to all 0, and then we pass all the zeros through the Hadamard gate. And similarly, we will initialize the ancilla qubit by to cat1, and we will pass it through the Hadamard gate also. So for an n qubit, if when we pass the n zeros through the n multi-qubit Hadamard gate, right? In that case, we will get, this is the output when we pass the tensor of n zeros through the Hadamard gates. Then we get this as the output, right? So what is this? This is basically the equal superposition of all the qubit, that is 1 over under root 2 raised to the power n. So x will be let's say if n is 1, it will be 0 and 1, just 0 and 1 only. So you will get cat 0 plus cat 1 divided by 1 over under root 2. So that was the case in the Deutsch algorithm for single qubit. But in the case in the multi-qubit case, so how many possibilities of the input is there? Let's say n is equal to 2, 4 possibilities, n is equal to 3, 8 possibilities, and so on. Like that, this cat x will have values cat 0 0, cat 0 1, cat 1 1, cat like that for 2-bit combination, and for 3 qubits it will have 8 combinations. So it is basically the equal superposition of for all the eigen bases, or the eigen or the computation basis basically. Now if Hadamard is seen to act, let's try to understand the Hadamard. When Hadamard gate is applied to the single qubit, we know that we will get it like this. In between there is a plus sign or minus sign depending on whether the bit here, whether the qubit here is 0 or 1. If it is 0, you will get plus. If it is 1, you will get minus here. And for a single qubit, it can be generalized to this expression. So there are 2 cases, but we can generalize it to this expression. Now for a multi-qubit, that means our n qubit zeros, when we apply the Hadamard gate, we'll get this value. Now the second stage that we do in the Deutsch Jozsa algorithm is the phase kickback. Now let's try to understand the phase kickback. What is phase kickback? When we apply the C0 gate to cat x and cat y, we get this expression cat x and y plus x, cat of y plus x. Now this is how we realize the circuit for phase kickback. We have cat 0 for, let's try to explain with a simple circuit first. So let us take two cases, cat 0 and cat 1. We apply cat 0 and cat 1 here as the input. We pass it through the header mud gate. This whole circuit is equivalent to this circuit, in which the role of the control, this is a C0 gate, but just the role of the control and the complementary function is reversed, right? In this case, our second qubit is the control qubit and the first qubit is our target qubit. So what happens here? When our for the cat 00 case, when the second qubit is 0, the first qubit will remain as it is. So for cat 00, the output is cat 00. For cat 01, so when the second qubit is 1, the first qubit is 0. That means the second qubit is the control qubit. This is 1. So the first qubit will be complemented. So that means 0, 1 will become 1, 1. 1, 0, second qubit is 0. It will remain as it is. Cat 1, 1. So that means the second qubit is 1. The first qubit will be complemented. So we'll get 0, 1. So this circuit only explains the C0 gate like this, where the second qubit is the control qubit and the first qubit is the target qubit. Now the same, just as we have explained it for 0 and 1, the same logic if we try to explain with the X basis or the header mud basis, like if we apply the C0 gate, this C0 gate is that gate where the second qubit is the control qubit and the first qubit is the target qubit. Now we apply in the header mud basis. That means if our second qubit is plus, the first qubit, there will not be any change in the first qubit, so it will get plus plus as the output. But if the second qubit is minus, that means it is equivalent to 1. So if the second qubit is minus, the first qubit will be complemented, so we'll get minus minus. If the second qubit is plus, the first qubit will remain as it is. If the second qubit is minus, the first qubit will be complemented. So if we have second qubit as plus, the first qubit is unchanged. But if the second qubit is minus, then the first qubit gets flipped in the header mud basis. This is called phase kickback. In general, this is the expression for the phase kickback. What is happening in this case? So this is our x qubit, this is our negative. Now what is our, let me explain here. We have applied the ancilla qubit as 1 qubit, then we passed it through the header mud gate. That means it is minus. The output of this header mud gate is basically ket minus. That means this is our, here let me just come to the point. This is our input. This ket minus is the ancilla qubit. So depending on the value of the ancilla qubit, you will get a phase kickback here, whether the first qubit will be plus or minus will depend on this phase kickback actually. So this is the job of the oracle. Now I'm just trying to explain the circuit here. The circuit, and I'm expanding the circuit now. How I am expanding? Let me explain. The n qubits are initialized to 0. The ancilla qubit is initialized to 1, pass through the header mud gates. So this is our quantum oracle. We get this type of output at the at ket x at the because the same input, whatever is applied to this point, we will get the same output as it is. But for the second, for this 1 qubit output, we will get y plus fx, right? Depending on, there will be a phase kickback depending on the value of the second qubit, which is ket minus. Now the similar thing. So this is the final expression, because at this point we get this as the output of the oracle. Now this output is again applied to the header mud gate. Here it is an n qubit header mud gate, But in the first algorithm, which is the Deutsch algorithm, only one Hadamard gate was there. So this input, which is the output of the quantum oracle, is passed through the Hadamard gate. So we get this output because the Hadamard, this is the expression, this expression is the functioning of the Hadamard gate. So this is the output that we will get after we apply, this is the output of the Hadamard gate, basically n qubit Hadamard gate, and we measure this input. If we measure all zeros, it is a constant function. For any other measurement outcome, f is balanced. The example is same. The Deutsch algorithm or Deutsch Jozsa algorithm are the same. Only difference is that in the Deutsch algorithm there is an input of single qubit at this point, but in the Deutsch Jozsa algorithm there is a multi-qubit input. We are applying n qubit input here, and we have initialized the n qubit input to all zeros, and rest of the quantum circuit remains the same, rest of the logic also remains the same. And we know now what is the goal that we are trying to prove with these two algorithms. As I was just trying to explain that the query complexity is the term that we will use to measure the performance of this algorithm. So what is query complexity? We have an algorithm, we will send our the details of the function to the oracle. Now oracle will tell us whether this is a constant function or that means this is the oracle basically. So it will give us these two outputs. One output is n qubit output, the other output is only 1 qubit output, right? Now if we let us consider the case of the Deutsch Jozsa algorithm. The function has got n qubits as the input and only 1 qubit as the output. I mean, we want to know that the function is a constant function or a balanced function. Now in the case of a constant function, it will give constant output for all the inputs. In the case of balanced function, it will give 1 for half of the inputs and 0 for the other half of the inputs. Now applying the same algorithm, if we do it through the classical means, we will have to make how many queries? We will have to make half plus 1. If we apply an input, n qubit input, how many possible inputs are there? 2 raised to the power n divided by 2 makes it half plus 1. So these many queries we will have to make in the case of classical computer, but in the case of quantum computing, we will have to make only one call to the oracle, which will tell us whether the function is a constant function or a balanced function, depending on this output. Just a minute. Depending on this output, when we measure at this point, if we measure all zeros, the function is a constant function. If we, for any other case, it will be a balanced function. I hope the point is clear, that we are trying to show the quantum supremacy over the classical computers. Thank you.